The energy of the natural world is entirely chaotic. In its rawest form, it is scattered, violent, and inherently disorganized. For centuries, we could warm our hands over a flame or burn wood to survive a winter, but we remained at the mercy of this heat, unable to harness its energy for complex tasks. That limitation remained until the development of thermodynamics, the formal science of energy transfer. The primary aim of this discipline is to take disorganized heat and convert it into a strictly organized state, mechanical work. Applying that single rule of conversion catalyzed the Industrial Revolution. Heavy machinery could finally translate the random kinetic energy of a coal fire into the precise, rhythmic output of pistons and gears. The exact same principles govern modern engineering. The thrust lifting a spacecraft relies on managing the intense heat of combustion to generate directed, organized momentum. The ability to efficiently organize heat into work provided the mechanical leverage required to build our global industrial infrastructure. Before scientists could calculate how to put that heat to use, they needed a method to mathematically isolate specific interactions. They start by defining a system, the specific region in space that an engineer chooses to focus on. Anything outside of that chosen region is classified as the surroundings. This is where the physical effects of the system are actually felt. Separating the two is the boundary. This divider can be a rigid wall, a flexible surface, or an entirely imaginary line drawn in the air. Add the system and the surroundings together, and you have the thermodynamic definition of the universe. By establishing these strict spatial zones, engineers can track exactly how much energy is moving from one place to another. Without these dividing lines, measuring energy transfer becomes mathematically impossible. Once the boundary is drawn, the system inside is categorized by what is allowed to pass through those walls. In a closed system, also known as a control mass, thermal energy and work can cross the boundary, but the physical mass inside remains constant. An open system, or control volume, removes that restriction. Here, energy and mass are allowed to transfer across the boundary. A power generation turbine operates this way, constantly taking in high-pressure steam and ejecting it after the energy is extracted. The third category is an isolated system. Like a perfectly insulated flask, boundaries are completely sealed, preventing both mass and energy from escaping or entering. Determining whether a machine is an open, closed, or isolated system is the first step in calculating how much work it can actually perform. To measure matter inside these boundaries, engineers rely on observable characteristics called properties. Intensive properties, like temperature and pressure, stay the same regardless of the system's size. Extensive properties, like total volume, depend on the amount of mass present. At a microscopic scale, individual molecules exhibit highly erratic movement, making absolute mathematical tracking for every single particle impossible. Thermodynamics addresses this through the continuum concept. Instead of tracking billions of particles, engineers treat the matter as a uniform, continuous whole and measure the average behavior of the molecules. This macroscopic approach replaces the unpredictability of molecular physics with reliable engineering data. A system becomes stable when it reaches thermodynamic equilibrium, meaning it is balanced thermally, mechanically, and chemically. When we apply intense heat or external work, we trigger a process, forcing the system from one equilibrium state to another. If a system returns exactly to its starting state after a series of processes, it completes a thermodynamic cycle, visualized as a closed loop. Because the net change in any property is zero, this loop can repeat infinitely to extract continuous mechanical work. This endless cycle is the basis for our current infrastructure. A nuclear power plant depends on these repeating thermal processes to provide a steady, reliable supply of electricity to the entire grid. These laws establish the governing logic of the physical world. By mastering these cycles, we've learned to direct energy transfer at a planetary scale.